Hola, 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 hello and welcome. Welcome to my vet journey by Dr. Melissa Judah. Don't forget to subscribe and hit the bell. ¡Comenzamos! Hello, this is Melissa one more time. Today we're going to be talking about the anesthesia machine and the leak test. We're going to be covering when to change the CO2 canister, when to replace the passive scavenging system, how to choose the correct breathing bag for your patient, how to calculate the amount of oxygen or gas anesthetic that you will be giving to your patient, and explaining how the gas moves through the anesthesia machine and how to do a leak test. When you're in the preparation room, the first thing you must do is look at your anesthesia machine. Look at it in the front and in the back. Look at it in one side and then in the other side. You want to identify the pieces attached to it, the type of oxygen tank, what type of breathing bag you're going to be using, and what system you will use. Try to identify the scavenging system and the CO2 canister. The CO2 canister is a white pellet that will filter CO2 from the anesthesia machine. It should be replaced after 10 hours of use. It can turn purple, but it may go back to white after each use. Another way to check if it's exhausted is that when you try to crush it with your fingers, the pellet should go into a powder easily. When the pellet is exhausted, it turns very hard. Next, we have the passive scavenging system, which will neutralize waste anesthetic gases. It must be weighted every time you use your machine and replaced after it gains 50 grams. Now the breathing bag. To choose your breathing bag, you will have to calculate the tidal volume. Tidal volume is the amount of gas expired and inspired in one breath. Tidal volume, or TV, equals 10 to 20 ml per K. Then you're going to multiply that by 6. Then you will divide by 1,000 to get the liter bag. Example. This is Maxe. He is a 30-pound dog. I'm going to divide that by 2.2 to get his kilograms. So he is 13.6 kilograms. We know that to get the breathing bag size, we're going to have to multiply the tidal volume by 6. So the first thing I'm going to do is calculate the tidal volume. So tidal volume equals 10 to 20 ml per kilogram. I'm going to choose the higher end, which is 20. So tidal volume equals 20 ml times 13.6 kilograms, which is Maxe. Tidal volume equals 263.2. So now with that information, I can apply that to my breathing bag formula. So my breathing bag formula equals 263.2 times 6. So I'm going to get 1,579.2. What I'm going to do next is divide that by 1,000. That way I can get my liters. I got 1.6, but I'm going to round that up. So Maxe will need a 2-liter bag. Now we're going to talk about the circuit system. To select the circuit, you must look at your patient's weight and physical condition. A patient that is debilitated or is less than 10 pounds will use a non-rebreathing system, but a patient that is over 10 pounds will use a rebreathing system. You will have to calculate the amount of oxygen delivered to the patient. If you're using a rebreathing circuit, you will calculate for induction 100 ml per K per minute and then decrease to 50 ml per K per minute for maintenance. This difference is because anesthesia can impair the patient's ability to ventilate effectively due to the anesthetic itself or because of muscle relaxation. Providing higher levels of oxygen at induction time helps prevent hypoxia, especially in early phases of induction. Anesthesia can also lead to low blood pressure and heart rate. Higher oxygen levels can help maintain the oxygen carrying capacity of blood and support better tissue perfusion. On the other hand, if you're using a non-rebreathing system, you will calculate 300 ml per K per minute. You will divide that by 1,000 and you will get your liters. Now I'm going to give you an example of the rebreathing circuit. On the left corner, you can see the vein system and a white piece. Now, let's use Max again. He is 13.6 kilograms. For induction, I'm going to use 100 ml per K per minute. That's going to give me 1,360 ml per minute. If I divide that by 1,000, I'm going to have 1.4. I'm going to round that up, and the oxygen level should be at 1.5 liter per minute in the first 15 minutes. For maintenance, I'm going to use 50 ml per K per minute. That's going to give me 680 ml per minute. Gonna divide that by 1,000 to get my liters, and that's 0.7. I'm gonna round that up, and I'll get 1 liter per minute that will be required for the rest of my anesthetic procedure. Another important calculation that you must have ready before working with your patient is the anesthetic gas requirement. MAC is the minimum alveolar concentration to prevent movement in 50% of your patients. The MAC for isoflurane in dogs is 1.5 and in cats is 1.6. The MAC for sevoflurane in dogs is 2.4 and in cats is 3.4. These numbers are constant, but what does that mean exactly? What that means is that for induction, you want to get closer to the 100% movement prevention. So if 1.5 is needed to prevent movement in 50% of my patients, where do I need to position my anesthetic vaporizer to prevent movement in 75% of my patients? Let's see an example of this. Let's have the isoflurane MAC for dogs, which is 1.5. So if 1.5 is needed to prevent 50% of movement in patients, where do I need to position my vaporizer in order to prevent movement in 75% of the patients? Let's do the math. If 1.5 goes to 50%, how much will be 75%? You're going to multiply 1.5 by 75, and then you're going to divide by 50. This is going to give you 2.3. You're going to round that up to 2.5, and that's where your isoflurane vaporizer should be in the first 15 minutes. Then you will have to decrease to 1.5 for maintenance. Of course, every patient is different and have different requirements, so you can adjust the vaporizer depending on your patient needs. But this is basically the explanation behind it. Don't be scared if when using sevoflurane, you're faced with a higher vaporizer concentration as compared with isoflurane. Sevo-MAC is higher as compared with ISO. Higher MAC and low solubility, which allows for rapid changes in depth at induction and recovery. So just keep this in mind if you're not used to using SIBO. Now we're going to go over the anesthesia machine. You always want to start from the green tank, which is the oxygen tank. It works at a high pressure of 2200 psi. Then we have the regulator, which is going to reduce that pressure to 50 psi, which is more suitable for the anesthesia machine. It also has a manometer, which tells how much oxygen is left. From here, the oxygen will reach the anesthesia machine through a hose, and then it can take one of two paths, either the flow meter or the oxygen flush valve. The first path will be to the flow meter. The flow meter will reduce the pressure even further to around 12 psi, which is more suitable for the patient. Here you can regulate the amount of oxygen that will enter the vaporizer. In the vaporizer, the oxygen is mixed up with the liquid anesthetic and formed into a gas. And from here, it'll go to the vaporizer outlet. From the vaporizer outlet, the gas will reach the inspiration valve, which is a one-way valve, then to the inspiration hose, and then to the patient. This specific machine has a vane system that is basically a tube within a tube. The inhale gas will run in the inner tube, while the warm exhale gas will run in the outer tube, acting as a passive temperature regulation device. Then the exhale gas from the patient is going to go to the exhalation hose and then to the exhalation valve. This machine has a manometer that will help you monitor the pressure within the system, and it shouldn't go above 20 centimeters of water. Then we also have the pop-up valve that allow the excess pressure in the system to escape via the scavenging system, where the waste anesthetic gases will be neutralized. This machine also has a pop-up valve. The scavenging system, this is a passive scavenging system, and it should be discarded after it gains 50 grams from initial weight. Then we have the CO2 canister that pulls CO2 out of the circulating gas, and the reservoir rag that will catch excess air from the system. Here you have a closer look to the vaporizer. In the bottom, you can add the liquid anesthetic gas, and then in the top, you can regulate the amount of gas that you're going to be giving to the patient. The second path will be the oxygen flush valve. Here, the oxygen will bypass the vaporizer to deliver fresh oxygen at about 50 psi. Next, we have the leak test. You're going to get all your equipment hooked up, and you're going to open the O2 tank. You're going to close the pop-up valve. You're going to occlude the end of the anesthetic tubing with your thumb. Then you're going to flush oxygen until the manometer reads 20 to 30 centimeters of water. You want to make sure that the manometer won't drop more than 1 centimeter per second. If that happens, then you have a leak. If you have a leak, you have to check the hosing, check the reservoir bag, check the CO2 granules, make sure they are screwed in correctly, and that the scavenging system is hooked up correctly. Then I also like to check my ET tubes by adding air with a syringe and making sure that my cuff stays inflated. Alright, that's it for today's video. I hope you learned a lot. If you did, don't forget to share, like, and subscribe so you don't miss out any future content. If you have any questions, please leave them down in the comment section. I'll see you in the next one. Until then, take care and stay awesome.